Hello everybody, this is Dr. Shambhavi and I am your course instructor for this course on Theoretical Foundations of Computation. We have had the first introductory class before, and what we did in our last class is to understand what the course is all about, what are abstract machines, and we've also learned a set of terminologies with respect to this course like alphabet, string, formal languages, and of how formal languages are different from the natural languages that we use day in, day out. So moving on, this is our first topic of the first unit, and what we will do today is to introduce you to an abstract machine which is called deterministic finite automata, popularly called DFA. What we will do in our next 20-30 minutes is to understand what is a DFA, how to design a DFA for a particular given formal language, and then we will conclude it with a formal definition of DFA today. So we will have a couple of problem solving session being done today. Okay, so let's move ahead. Let's try understanding the DFA in a very vague form. Okay, so let's visualize a DFA to be a tape which has multiple cells in it. So if you can see here on this diagram, I have a tape which you could imagine to be an infinite tape, and each component here is called a cell, and within the cells I have symbols, right? Symbols or alphabet. Alphabet popularly denoted by sigma, right? So as you can see, the example here has a tape which is with the alphabet of zeros and ones, the symbol of zeros and ones. So you could imagine that your DFA is this finite control machine, the abstract machine, which...
See, whenever you want to construct an object and you want to create the drawing in 3 dimensions, probably this is how you create it, right? If you look at this object shown in the drawing, the object has got height, it has got width here, it has got even the depth. The moment I try to represent a 3-dimensional drawing on a 2-dimensional paper or a sheet or a screen, what happens is distortion creeps in. Since we do not have the depth aspect of it in a 2-dimensional board or a paper, the shape of the object gets distorted. And it's very critical in the field of engineering that while constructing an object, we require true shapes and sizes of the object. Therefore, preparing a drawing of this type doesn't help. Think of a very complicated object and you try to represent that in 3 dimensions. You will not be able to identify what would be the shape of that particular portion of that complicated object. It becomes extremely difficult for the end user. For example, in a shop floor, when a worker has to create the object, looking at the drawing, he may not be able to understand the details of that particular object. So that means when we try to represent an object in its 3 dimensions on a drawing sheet, some of the details that are required from the perspective of construction or manufacturing gets lost. This poses a big challenge for the end user, like in the case of a civil construction field. The contractor may not be able to understand.
Good morning all of you. I am Dr. Savitri Bhatt and I am your course instructor for signal transduction, which is an elective course offered at 6th semester. To begin signal transduction or cell signaling, let us have an idea about what is cell signaling, and then we see a pathway of glucose regulation as an example. So, cell signaling is divided into 3 steps. One is response, second is the transduction, and the third one is the reception. So, the reception is the first step in which we have a ligand Ligand can be either a biological molecule, biological system, or it can be a chemical, or it can be a physical ligand, which is in the form of, like for example, physical means it can be a temperature change in and around. Biological, the best example is COVID-19 virus, which binds to the specific receptor on the cell. And then we can have certain chemicals also in and around our atmosphere or environment, which binds to the receptor, and downstream signaling happens in the cell. So the first step in the signal transduction is reception of the signal. So that happens from the outside to the inside of the cell. So there will be receptors present on the membrane or inside the cell, which will receive these signals, right? And these signals can come in different forms. These signals are then transduced inside the cell. Transduce means there will be lot of cascade of events happening downstream, and that will lead to generally phosphorylation or dephosphorylation and activation of certain other molecules, specifically second messengers like cyclic AMP and all. And then we have the final step, that is a response. So the response what you get will be with respect to whatever ligand is bound to this. Like for example, if you have a
welcome to the course on interfacial phenomena. Last class discussed about application of English equation. So in this class we will discuss about supersaturation and capillary condensation and important topics of interfacial phenomena. So prior to that, so in the last class we discussed about applications of Young-Laplace equation and Kelvin's equation. So the Young-Laplace equation, it relates to the pressure difference to the shape of the surface. For the sphere the pressure difference is different, for a flat surface and for a cylindrical surface it is a different. And this is a generalized Young-Laplace equation, which is delta P equal to gamma. Gamma is surface tension by 1 by R1 plus 1 by R2, where 1 by R1, 1 by R2 are nothing but curvatures, or R1 is a radius of curvature and R2 is a radius of curvature. So they are the principal radii of curvature. And Kelvin equation gives us the quantitative information on the effect of surface curvature on the vapor pressure. So whenever there is a surface curvature, so what is the effect of that on the vapor pressure of the liquid? Remember, vapor pressure for the liquid, the curvature. So this was the equation for Kelvin equation. I mean, this is the Kelvin equation where we have PV by Psat. Psat is the saturated vapor pressure, which is equal to exponential of 2 gamma. Gamma is the surface tension and V bar L is the molar volume of the liquid, or universal gas constant. T is the absolute temperature, Rd is the radius of droplet. Since we cannot measure molar volume of the liquid, that has to be related to the known quantities. So here that has been related to the molecular weight of the component and density of the liquid. And 1 by Rd is nothing but a radius of curvature, 1 by Rd is nothing but a curvature, which is h. So by making use of this equation, we can determine the